Yeah, by the time he sets, maybe I'll say. So I will probably be talking about the third flavor. Although the goal of all these three is the same, the terminology is quite different, and I think the complexities are different. And this will be a interactive kind of a session. So I want some participation from you. I will also ask questions in between, and you are free to express what you feel about that. Which screen do you prefer? I'll also write few things on the board. They vote for this one, so I'll. Okay, so since they said things first, maybe I'll. So this is more of a pedagogical lecture. I'm not going to flash results in today's lecture where people have used machine learning in doing something about convection. Maybe that we'll reserve for the next lecture, the next 1 hour lecture tomorrow, I think. Am I online? Yeah. Okay, so yeah, thanks a lot to Adway and other organizers for giving me this opportunity. I am going to talk about atmospheric convection, as I told you, and how it is represented in models. You might want to notice that I'm trying to not use the word parameterization, which is, although it is used again and again in the community. So I want you to actually make some notes while looking at the video I'll be playing. And I want you to make your kind of document your thoughts about what should be done to really represent this type of a flow. You have heard quite a lot about 2D flows, 3D turbulences. Maybe yesterday you may have also heard about oceanic turbulence. This is, so the animation will be about cloud. I want you to note down what all should be, what all one will have to do so that we could represent this system. Yeah, that's the exercise. And the goal, I think I have mentioned this already. So let me play this video. Yeah, so the point I wanted to probably make was, okay, so I'll probably give you a running commentary of what I wanted you to do. I'll probably do is, so as you will observe, you would have observed the clouds within a kind of time span of few hours would develop vertically and also like a kind of fluffy thermals rising up. So I wanted you to kind of say that there were thermals, that they were to grow very fast in the matter of few minutes to few hours. The bottoms are quite flat. I wanted you to also say that since mass was going up, this mass, somewhere it should subside. Just that only the rising mass is being visualized. The same mass is subsiding somewhere else. I think these few key elements will come again and again while we talk about parameterization. So I was hoping that we would have defined these as the so-called updrafts. The subsiding motions are not seen. So it could be that all of this mass that goes up might actually sink down just next to the cloud, killing the development of next cloud, adjacent cloud. It could also be that, does it work? Oh yeah, yes, thanks. So, okay, so these updrafts, downdrafts, the mass has to come down. Where does it come down is a question. And maybe there are regions where there are no clouds and hence we don't know what's happening. Is the air sinking by and large from the top, or there is hardly any? We can be sure that there is some turbulence there, which we are not able to visualize because there is no condensation. In the second animation, I wanted you to observe 3 different layers, which when it comes, I'll point out. You will see that as the cloud develops, the bottommost layer, the clouds move in a particular direction, whereas the topmost layer goes exactly orthogonal to it. So there is also some vertical shear associated with the cloud. So clouds, while they develop, get sheared off and goes in totally orthogonal direction. So while it is probably interacting with its surrounding, it is also doing something to the surrounding. So there are two-way interactions. That's what I wanted you to appreciate. So there is cloud and circulation interaction. The third animation was about was a global map where I was going to show you animation of clouds evolving over few months. And there I wanted you to see the difference between how the life cycle of clouds in tropics versus away from tropics. Away from tropics, you have much larger covers which sustain for long times. In the tropics, you have popcorn-like clouds appearing at a particular location and going away. So there is variability in terms of what clouds kind of sustain, how they ride on top of the background vortices. That was the thing I wanted you to appreciate in these three animations. And the fourth slide, is it working now? I think I have already probably done the. So let's with this. Yeah. Let me check if this goes forward. Yeah, yes. Okay. So I think we probably, I assume that you guys would want to see this in the free time later on. So that the clouds develop, there are key elements of clouds. Air sinks. So there is cloudy air, there is sinking motion, downdrafts, and there is so-called environment where we don't know what happens. These are the elements. And then they have flat bottoms. Below the flat bottoms are the thermals, which we are not able to see, which will materialize as clouds. So there are many things which we are not seeing, but ultimately lead to the variability. In one of the animations, you actually do see something just below, which I wanted you to notice. Okay, so what is convection? Convection is transport of heat, moisture, and momentum or other properties within a fluid due to the bulk motion of the fluid. How many of you have heard of this before? So it should happen within the fluid. For example, one key question would be, maybe I would like to hear is, how is, let's say I have a balloon which has some gas which is lighter, so that I create density difference, and I just release it. So balloon going up, how is that different than convection? There is density difference. Yes? There is no transfer of heat. Adiabatic kind of convection, no transfer of heat. Yes, buoyancy is required in convection. Buoyancy, in next slide is going to be buoyancy is essential. In convection, buoyancy is there. Does anybody else? The mass is isolated, the gas is different, right? The inside one. So it's not within a fluid, it's not emergent within the fluid. So that's one very important property, that it should be emergent within the fluid. Some part of the fluid should start having lesser density. That's one of the key. The other one is it should have buoyancy forces which would act against gravity. One of the key difference, usually people say, if the fluid was moving horizontally versus vertically, what is the difference between vertical advection and convection? And somebody said, there is maybe not necessarily presence of buoyancy. So vertical advection could happen just because of the flow, whereas convection always happens because of buoyancy. Yes, we will want to define buoyancy in the next slide. So there are these three things to remember about convection. That it is from the same fluid, part of the same fluid. Second, it is associated with buoyancy and always against the gravity. That's how rather it is defined. And it is all driven by density gradient. So in some sense, let's look at the left-hand side plot. Let's say if this was moon, would you see much convection? There's hardly any kind of matter, right? I mean, matter is there, probably fluid on the moon, right? Maybe very thin atmosphere. I don't know how thin, but very thin, maybe centimeter or so. So hardly any convection there. So you need a fluid, and without a particular fluid, convection is not possible. That's another one. Okay, so what is buoyancy then? Can somebody say? We said buoyancy is required, but we haven't defined it. Anyone? Yes. Yes, yes, against the gravity, yes. So he's saying there's density difference. So a good thing, one good way to think about this is there's some chunk of fluid, and this chunk of fluid starts feeling, let's say, lighter in this particular example. And then this chunk of fluid will want to then, because it feels lighter, it will have the upward force. But along with this is part one of the answer. The second part is it will want to push fluid above. It has to push fluid sideways, right? It has to push fluid from A to A1, A to A2. This fluid so there will be more fluid here. So there will be higher pressure there. And because of mass conservation, the pressure here has to be lesser, and the fluid has to converge below and diverge above. So convection and buoyancy just is in isolation not sufficient. The effect of convection, that is pushing fluid, is part of the convection. That's another concept we should remember. These all, you will realize that these all will become important in the parameterization. Or even tomorrow, if you want to use machine learning, you will want to use these elements, key elements, as the potential predictors or key constraints, loss function. It will come. People have tried doing this sort of a thing. That's why I'm introducing it. So the fluid being pushed is also part of the convection. Okay, so let's say that you have some fluid. These are called typically Rayleigh-Bénard convection problem. So you have some fluid, let's say you take some water in the kettle, you start heating it from below. What do you see typically? The bubbles would form. At one point of time, you might see some hexagonal structures like that, although this particular image was not from water, it was from some other substance. So you see these hexagonal structures from top, and if you keep on heating it, at one point these bubbles rise up vigorously, and you get, you say water is boiling, right? So this is also in some sense some convection going on. If you take two parallel plates, one at higher temperature, another one at colder temperature, and you observe the motion in between the plates, typically you see such rolls. They are called Rayleigh-Bénard rolls. The interesting thing here is they are quite symmetric. So rising part and subsiding part approximately has the same area, same mass flux. In your experience, do you see something similar in the rightmost case? Is the mass going up and mass coming down? Is it similar? Yes? Right now, we are not yet in the ocean, just in the boiling pan. Yeah. There, do you see the mass going up and going down similar? So far as convection looks like that, that means you see those hexagonal structures. Maybe the mass going up is equal to mass going down. But the moment you see that bubble, which vigorously develops, there is an asymmetry in the system. So the mass going up, the rate of that and mass that will have to balance changes. One way to find out as to what will happen is through Rayleigh number. I don't know if this came before. I know Rossby number came in, Reynolds number must have come in. Rayleigh number, was there any discussion before? So Rayleigh number, very crudely again, you could define this much more formally from scaling. But Rayleigh number is time scale for thermal transport via diffusion to time scale of thermal transport via convection at some speed. So if, let's say, if this fluid was not water, but let's say old sambar or some jelly, you would expect much more energy before you could really generate these rolls, right? So it's a function of viscosity, so transport via diffusion. And if you were to have some motion which carries stuff up and down, when that develops, then you will start calling it convection. And typical Rayleigh numbers, that means the ratio of time scale. This is when the diffusion time scale is very large and convection time scale up-down motion is relatively small, then you get large Rayleigh numbers. And for a dishpan convection, it's already 10 power 4, 10 power 8. For the real atmosphere, it's even larger, up to 10 power 12. So and beyond. And one of the reason is the length scales in atmosphere are quite big. So in one of the later slides, I'll just say that this is different than what happens in the atmosphere in terms of scales. And another important point that I wanted to highlight here was it's still the same fluid, either there or here. It's still the same phase of the fluid that is doing the mass transport. This will become important when we want to compare this with moist convection and want to write few equations for that. Okay. Yes. Yes.
Is thermal transport via diffusion what convection is? Because diffusion doesn't sound like convection.
No, that's what I think is a part of Rayleigh number. The Rayleigh number, because it's the time scale, right? It's not the, yeah. So long time scales for diffusion, fast time scales for convection. Okay. Yeah, let's go to, so engineering, so atmospheric convection versus engineering convection. That atmospheric dry convection has Rayleigh number of 10 power 12. And another key difference from what we have been just experiencing here is that both temperature and pressure decrease with height. So you cannot just compare air masses, let's say at 1 kilometer and at surface. You could do that a bit for ocean at times. But for atmosphere, the density is a function of both temperature and pressure, much more stronger function of temperature and pressure. So that means for you to decide as to what will happen to a chunk of mass, how much will go up, how much will come down because of this buoyancy force, you cannot just use density because it itself is a function of T and P. And a joint variable of T and P is called potential temperature, which is a nicely, if you like, weighted function of temperature and pressure, so that you could compare air masses at 1 kilometer or at surface. Okay, so one typical way of asking will convection occur or not is to take an air parcel and perturb it a bit. As a simple case, you could do it adiabatically. That means assume that the amount of energy with the parcel remains with the parcel, and check and see if it's stable there, or if not, it may want to come down. So one typical way, again, now I will increase the speed a bit so that we ultimately reach to writing some equations, considering we lost some time at the beginning. One very typical way is to do something called parcel method. So where you take this imaginary parcel of air, which is, so how many number of molecules there are? Large enough to kind of not worry about the mean free path and so on. It's large enough, but small enough so that you could consider it infinitesimal and then write your differential equations on that. So that much chunk of air, and then you displace it. If it's heavier, it will want to come down. The relevant density parameter here is the potential temperature instead of the real density of the fluid. That is the atmosphere. If theta increases with height, we will say it's stable. If it's not invariant with height, that means whatever it's here, if you were to push it, it might still not care as much. In that case, it was feeling it much higher, heavier than the environment. In this case, it will feel lighter than the environment. So you could essentially define will convection occur by looking at the vertical gradients of theta. Okay, so what happens when the air is moist? So until now, the thing was much more symmetric. The mass goes up, mass comes down. My main point in telling you what happens when you add moisture to the system is to tell you that you get lot of asymmetry in the system and lot of if-else things start creeping in. Let's look at what really happens. Let's focus on the left-hand side. You have a specific humidity profile, Q, which exponentially goes down with pressure. So pressure is highest at the bottom, lowest at the top. The decay is exponential. This is the saturation condition. QS is the saturation condition. So at near surface, if we were to take this parcel up, exactly push it up, then at that particular level, it will want to feel condensed. So because it will reach the saturation. So the question of will convection happen? If you have enough buoyancy in the boundary layer, maybe in this layer, it's the moist air, but it still behaves as if it is dry because you don't have to worry about condensation. So you could just say, I will just look at the property theta of this air and find out if the theta is decreasing or increasing with height. And I think I mentioned that theta decreasing with height is unstable. That means if you were to push air mass up, it will want to go up. It's an instability. So such description can suffice in this layer. But once you reach the level of saturation, things become quite complicated. So which is typically called conditional instability. So some air masses, so let's think of the real situation. In reality, you will not have air masses which look the same horizontally. Some air masses may have much more water content than the other air masses. They might be much more drier. So if you were to push both of them with the same kinetic energy that your buoyancy allows, then in one, depending upon its water vapor content, might saturate while the other may not. So for the same given environment, some parcels might feel saturated while the others may not. So this is where if-else condition starts. So you then call it conditional instability. You tell me what is the content of the water vapor, and in the Lagrangian sense, I can tell you at what altitude it will saturate. In general, it may not. So if the adjacent parcel was not having as much water content, then it might still be stable, whereas the one with moisture content might be unstable. Okay, so that's typical. So you could divide your kind of this phase space of temperature versus altitude given the background conditions. You could say for this particular parcel, situation is either stable, unstable. You could define such criteria. Okay, let's move on and look at, I think this you might know, just that, yeah, so you typically have conditional instability. I guess somebody must have mentioned QG. I think Jim has mentioned QG theory. One intuitive way of pursuing this further would be, like QG theory, you might want to do stability analysis of the system. That would be a more elegant, like very elegant way of doing it. Just that there are two kind of bottlenecks. One is that perturbation and stability both depend on both temperature and humidity. So it's in two variables. So things become quite complicated. And stability condition depends on finite amplitude perturbations. This is where the conditional nature comes in. If I am able to push this particular parcel up with as much energy, how much energy do I give? The stability analysis might depend on that. If it's sufficient enough to reach saturation, then you have to worry about one type of analysis. If not, then some other type of analysis. That's what kind of, I would say, puts a spanner in doing a stability analysis of such a system. Okay. So what really happens? Typically, meteorologists, atmospheric scientists look at this skew-T log P. So this is the theta axis, where theta constant lines are these ones, the red ones. And y-axis is the log P. And I told you, right, initially in the boundary layer, even if you have water vapor, so far as it does not reach saturation, you need not worry as much. Maybe if you work on fog and if you care for lifted, I mean, some phenomena which are affected by radiation, considering water vapor is the key radiation component, you may have to worry about it. But by and large, for convection, you can just say, my air parcel with a particular theta will keep on conserving theta. But once it reaches the lift-in condensation level, that means it feels saturated with respect to environment, it will release the enthalpy of this chemical reaction, right? It changed its phase. So it will release some amount of energy. And that much amount of energy will be used to warm itself. I guess you may have heard this part of story. So I'll kind of keep it short, that it will keep on fueling itself, will going up, up, up. Okay, so there are two key quantities. One is called, so until here, the environment was, which is like that, the leftmost curve, was still not favorable for convection. Although your parcel was condensing, generating a bit of buoyancy, but it still had to counter the environment. Environment was trying to push it down. So if your parcel, because of either turbulence or large scale features, is able to navigate through this discouragement, which is sin, convective inhibition energy, then it can reach level of free convection, LFC. Level of free convection is a relatively nicer state. That means beyond that, your environment will not want to discourage you. Instead, if you were to condense a bit, you could utilize that much amount of relative buoyancy and keep going up. This is the usual way of thinking. So people usually define CAPE as the relative energetic kind of difference, integrated buoyancy, if you like. CAPE is convective available potential energy. Amount of energy the parcel does have as a potential that could be converted into kinetic energy if it were to keep on getting this buoyancy and converting that into kinetic energy. There is one key kind of bottleneck in whatever I said. Is anybody able to pinpoint to that? I just said it, that if it were to keep itself saturated, it will keep going up, up, up. And then it doesn't have to worry about anything about the environment. Yes, that's an important point. That I assume that the environment, which was the leftmost curve, it will remain as it is. Although this particular parcel is interacting with the environment, right? It's also emitting gravity waves. It is interacting through the edge turbulence with the environment. So two things will happen. One, the background profile will change within the time scale. And second, because of the phase change and the corresponding, I told you, right, divergence and convergence, it will want to entrain some fluid inside. I don't know if Professor Rama mentioned about this, but this is a key process, that while it wants to go up, it also entrains some amount of fluid, surrounding fluid. And in the process, it may not exactly follow this. At every instance, its state is variable, depending upon how much fluid it entrained from the surrounding. Yeah? So the moist convection will have to worry about, will parcel from surface reach this level of lifting condensation level with turbulent kinetic energy? Will it be pushed there? Will it be able to overcome the inhibition? And will it feel saturated throughout against the entrainment? I did realize that I have written the third point on the board, but yeah. So that's what I think we will have to worry about when we think of convection. You will realize that unlike in the dry convection where things were much more symmetric, since we haven't played animation, let me tell you that things get quite asymmetric in moist case because of all of this. Adjacent air parcels behave differently. Their saturation criteria is different. The amount of entrainment that happens is different. Although they might see similar background environment. All of this makes quite a lot of difference in terms of representing it. The second point I want to mention is, we haven't discussed this in any detail, but the enthalpy of this chemical reaction is so large that you basically warm up the whole of the column such that the subsiding air, which will have to compensate, right? I told you, right, that the mass going up will have to come down. This cannot maintain the same aspect ratio. That happens for dry air. In dry air, we saw those rolls, right? Typically, people see rolls or cells, but mass rises up and mass subsides down in the near vicinity. In moist convection, the ratio is approximately 1:10. So if air mass rises up, it has to have around 10 times more area such that it can subside and radiatively cool. This constraint comes from thermodynamics, which we call radiative convective equilibrium. You could look it up, radiative convective equilibrium. That it's asymmetric. The ratio is quite asymmetric. Okay. So let us, I'm going to kind of make a switch now. So I've told you what convection is. Now let's worry about how people have tried parameterizing it. But before that, let me kind of just say that, just make one point before we go away from. Let me just draw that cloud, whatever, with flat bottom, right? That you should have seen in the animation. And the key point I wanted you to notice, which will become very important in our next lecture, where I will tell you that this has been one of the biggest hurdles also in kind of incorporating machine learning, replacing such parameterizations with machine learning. So what typically happens that you would otherwise see in the video is there will be eddies which will go in all different ways, but there'll be length of the eddies will be all mixed. So in the same 20-minute development, some eddies will just mix across adjacent layers, but a few others will kind of develop quite a lot. So in the same 20-minute time scale, you would see them having all this full gamut of motion. And this becomes quite challenging. And also one of the reasons why convective parameterizations then take significant departure from typical CFD solvers. So typical CFD solver for this would want to cover this with mesh, right? Say you divide this in whatever geometry you like, your numerics likes. And then you say that at one time, in one time step, the adjacent is between two adjacent grid boxes. And the flow, whatever happens, will be resolved through such a process. It will so happen later on that if we were to use the same philosophy, we may not be able to resolve dynamics. That means one would require to resolve what happens in 20 minutes. You will want a resolution of a fraction of second such that you could resolve all of these eddies. And then in the whole simulation will be for 20 minutes, like in the case of direct numerical simulations or large eddy simulations. Then if we were to care about the flows, that means this particular cloud would ultimately generate pressure differences at different altitudes, depending upon how much heat was released and how much of that got into pressure gradients. It will want to drive flows. Those flows will have length scales of thousands of kilometers. And if you were to care about those flows, 20 minutes is the minimum time step that you can afford. So on one hand, you want to resolve all of this. But on the other hand, you also care for the flows that this drives or gets driven by. I told you, it also rides on these vortices. So there's this discrepancy between these two phenomena which we really care for, but their timescales are different. Okay, so that's how also I will want to end this lecture so that we motivated enough for tomorrow's lecture. Okay, let's do a transition into what is parameterization. I think since Vishal has mentioned this, I'll just say that this word parameters typically used in the nonlinear dynamics literature. I've taken this example of Lorentz system. The sigma, rho, and beta would be the parameters, right? They came out of scaling. So they are ratios of few things. So they're ratios of physical forces or heat transfer quantities. So sigma is Prandtl number, which is a ratio of momentum diffusivity to thermal diffusivity. So these two parameters gave this particular parameter in this system, right? And then the rest of the structure of the system is known. Its momentum equations are coupled to some thermodynamics equation. So you then know what sigma, rho, and beta is, and then you think of it in the real parameter sense, right? Maybe Vishal must have mentioned this. So I'll skip this. Unfortunately, while studying moist convection, we don't know such a system as to what is this minimal system, which represents whatever I just described in language. So we don't know a complete description of system or parameters that govern that system. I did tell you that Rayleigh numbers are quite large, but Rayleigh number alone is not a sufficient description of what goes on. We don't have a good numbers to describe, say, radiation to convection ratio or phase change. We still do not have such kind of defined it a closed form system such that we could then say, oh, these are parameters. Let me then ask a question, how much do they vary? Is there a critical nature in the system based on the parameters? So instead, what we have to do is, I think I'll just skip this. What we have to do is then take a very different view. We will say it's a technique. You can already see we have gone farther away from being very rigorous, right? We just said it's a technique so that we will quite relaxed, used in NWP to predict collective effects. It's also quite English, right, than math. Of convective clouds that may exist within a single grid element as a function of large-scale processes. So that means there is already a sentence that large-scale processes have a particular grid. I have a grid in mind, and I don't know how to worry about clouds in that grid. And since I don't know about it, I'm going to use a technique to represent its collective efforts. You will see also subgrid scale representation, parameterization, and there the hidden notion again is that is to ultimately look for such a closed form set of parameters. That's what you want. But since we don't know enough about the system, we name it parameterization, but it is not exactly same as what the typical descriptions done in the nonlinear dynamics community. This is a very interesting paper to read, those who want to read more. So in cumulus parameterization problem, we are concerned with statistical behavior of such cloud ensembles using different large-scale conditions. So that means for the whole of this cloud cluster that I showed you, you will just have kind of one particular value, say of temperature, of humidity, of wind, for the whole of this cloud cluster. And I will be asking you, can you, as a function of these single kind of variables, can you represent whatever happens within one grid? That's the question I will ask. In this sense, the climate models run through this loop where you have moist convective processes which transport mass, heat, and momentum upwards, which feeds back onto large-scale processes through the pressure gradients. Through pressure gradients, you have flow adjustment. Flow will transport heat and water vapor and whatever traces. That will generate a new state. That state you will have to check for convective instability and in a column. So the column thinking and horizontal thinking is quite decoupled. This is very different from typical fluid CFD. You don't have to worry about vertical versus horizontal. The CFD will, since it's a constitutive, laws are written on every grid box, and you solve it at every time step. You worry about how much energy is lost from one grid to the other grid, from one above, below, and horizontally. Unlike that, you will want to do something asynchronous here. You will want to do something very fast in the vertical and something relatively slow in the horizontal. Yeah? Okay. So let me skip maybe some of it. considering I have less time, and I do want to show you how people write stuff. So I'll just skip some of it. I think we have made a good description of what all goes on. There is typically updraft. This is kind of convection in as much glory as we know. Maybe I cannot claim that this is a full set, but there is many things going on in the boundary layer. Cloud masses rise up. Sometimes they form stratified layers called anvil. Sometimes if they have form condensate in it, then the properties work one way, while the condensate, if it's heavier, may want to fall down in its journey. It might want to re-evaporate if it faces a drier environment. If it does so, then there is again thermodynamics, heat exchange between evaporation of falling raindrops, and it will cool that air. That air might want to fall down because it's cooler and denser, and hence may want to form these cold pools. These cold pools are density currents which will fall down and kind of smudge over the larger area. These cold pools sometimes also collide. Cold pools from two convective systems collide, sometimes give rise to new convection. Sometimes this cold pool generated gravity current interacts with the background vorticity. I'm saying quite a lot of things. I hope you understand what all goes on in just one grid box. That all we will want to represent for such a system. Sometimes there are congestus clouds which are not as tall, but have kind of have much more interaction with the surrounding air through entrainment. There are sometimes cumulus clouds or stratocumuli, which is driven by radiation much more than anything else. Okay, why do we care for such a representation? See, if there was so much going on, but can I just put a constant there and be done with it? That would be the first thing one would want to worry about. What people have, so just to motivate that, I will show you 4 panels. So this is ensemble mean of 25 CMIP models, and all of them show rainfall biases. You can see that these rainfall biases go as big as, there's significant rainfall biases. We haven't yet developed a notion for how big is 3 millimeter per day. So I'm not going to tell you that this is quite large, take my word. Either in 25 CMIP models, or if you then embed 2D CFD models within a climate model grid box. So you say, oh, I know that there are these 2 different time scales. What I do is instead embed one 2D model which cares for all of this, all of these eddies, embed it inside a climate model, and then run them asynchronously. People have tried doing that. That model also has a lot of error. If you were to say, I have huge amount of compute power, I will resolve all cloud clusters larger than 10 kilometer, as if like a large AD, I'm resolving some part of what goes on explicitly. So my CFD will take care of what all goes on in some detail. Even with that, you are not able to get precipitation distribution. This is typically ERA 5 reanalysis, where it's a model output, but has assimilation, observations assimilated into it. So all of them have a lot of precipitation bias, and the key reason for them misbehaving is convective parameterization. So let's look at 4 parts. What needs to be represented in a climate model? Can diffusive models help you? What sort of non-local transport people have been thinking about? So people have asked this question. People were aware of all of this. I will tell you what they have been thinking about in the past. And the key question would be, how can machine learning help ultimately, considering the context of this workshop? Let's start with a simple set of, how many of you know Reynolds transport theorem? Oh, none of you. Couple of you, okay. So I'll probably not be able to write all of that, but I'll just say you could, for any variable, so I am just going to write generic representation. Phi can belong to, say, temperature, humidity, some components of wind and so on. Yeah, whatever you want. Reynolds transport theorem tells you that you could write the conservation equation this way. This is what climate model solves for. Dou x of u times phi plus dou y of v times phi plus dou z of omega times phi, and all the sourcing terms I'm just saying as phi. So here you want to put this in a climate model. Climate model has a particular grid box. So a grid box, let's say of typically 50 kilometer. So I have climate model of 50 kilometer. So that means this full variable, I can resolve it only up till 50 kilometer resolution. So I'll just say, I just divide this as 50 kilometer and whatever is the unresolved. So this is also called Reynolds decomposition. Yeah. So in the climate model context, we'll say resolved part and unresolved part. We will do this for all the three variables plus u prime. I'm not writing all of them. What you can show is this then can be written as, so now all of them will have bars. So that means my climate, whatever my climate model does, I will write on the left hand side, u bar, e bar, e bar, phi bar, plus, this is explicitly resolved, right? So think of again cloud cluster. The mean ascent in the cloud cluster and the transport associated with such a cloud cluster is here. That climate model resolved at some 50 kilometer resolution, right? That is resolved here. All the unresolved part, u prime phi prime bar, v prime phi prime bar, right? Sorry. Yes, yes, yes. So all of this is not resolved, right? Typically what climate models do is phenomena such as gravity waves, which are horizontal part of the turbulence, things such as sub-mesoscales in the atmosphere, they all are here, but in the sense of horizontal. So these are actually not represented, not thinking that they are not important, but at the scale of 50 kilometer, the most dominant component comes from the last term. So that means the vertical term, right? We drew a cloud and saw all of this. So the key aspect of then doing parameterization is to write this, write W prime. So parameterization is about writing this W prime phi prime bar as a function of P and whatever, right? This is resolved, P bar, sorry. This is resolved. Your climate model will tell you how this is evolving. You want to write down all at much smaller length scale as a function of what you resolve. Yeah? Okay. So can diffusion work? I think you can clearly see what will diffusion do. Diffusion, let's say you have this water vapor profile, right? So you are trying to take this much amount of water vapor, so Q as a function of Z. Diffusion will want to take this much amount of water vapor up, from the upper layer, some amount of water vapor down, between adjacent layers. It will want to just reduce the gradient, right? Make it zero in the perfect case. If this was non-local, that means if you were to carry this as a part of convection, if those thermals were to rise up and mix with something else, then those properties are actually carried and they will mix with, so the environment there is quite dry, but your thermal is carrying these properties. So these are then called non-local. It's not between adjacent layers, but between non-adjacent layers. So diffusion is not a good model. Instead, one has to worry about non-local transport. And there are two celebrated models for such a non-local transport. One of them is called mass flux based model. So I'm trying to look for, say, maybe here, mass flux based model, which tries to write this W prime phi prime as contributions from updrafts. So W prime phi prime updrafts plus W prime phi prime downdrafts plus W prime phi prime from environment. So you try to decompose this in terms of these key elements that do the transport, updraft, downdraft, and environment. And then you say, in the updrafts, how much amount of mass flux this W prime exists? Is it where these parcels more buoyant than the surrounding? You ask such questions. Typically, this is written as a function of, so you could write this as a function of two parameters in this kind of way of writing it. You will write this down as a function of cape and mass flux, cape, which will give you ultimately mass flux. So all of this is written as part of the cape that we saw before. Yeah. So you would want to write it this way. The other way, which is not mass flux based, you don't care for what were the key ingredients of what happened, up and down and so on. You instead worry about what is the net goal of doing this. You say that what type of clouds happen, at what level do they do transport, I don't care. Instead, what I care for is, this was the water vapor profile before. After whatever happens, how does it look? Right? So if this was a water vapor profile, if after convection, if this were to dry, so that means water vapor were to be carried up, so this will dry and that will moisten. If it were to be that, then the other way of doing it says that you just relax this to that. And that means what is required out of all of this, I just have to take a reference profile and then find out the tendency between the new profile and the old profile, and then you are done. Yeah, so this is called relaxation type. The first one is called mass flux type, and the other one is called relaxation type. Okay, I think there is also the third way of doing things that people have worried about, which we will probably not discuss. I'll just tell you what they did. Like you wrote a conservation equation here, people tried writing conservation equation for this. So that means you write a conservation equation for W prime theta prime bar. How can you get there? You have these equations, right? You just multiply here with W. So you write equation for phi prime, multiply here with W prime. You have equation for W prime, you multiply that with phi prime, club all of them together, write a conservation equation here, run large AD simulations, learn what happens to higher moments. That's what is called representation through higher moments. You use large AD simulations to train such kind of write down physical form of such equations. All these three are currently being kind of tried out as a kind of so another way of machine learning way of saying this would be to find surrogate models, right? You would say, can I write a surrogate model? People are trying to do either replace cloud model or take some insights from the higher moments and tune parameters, or just fully replace them. Maybe we'll chat about them in the next lecture. Yeah, I think probably I'll stop with that.
Okay, thanks, Vishal. Questions? Questions?
So thank you for the insightful talk. My question is simple. Why the cloud bases are flat, sir?
Why the cloud base is
Bases
black?
are flat.
That has answer in radiation actually. When the cloud contains liquid water, the bands which it emits it looks black basically. When it is nimbus, it looks black. It looks shiny white when it has ice.
Hi, sir. I'm Deepak from IIT Roorkee. So, in the previous talks, Professor Rama has mentioned about the microphysics, like all the microphysical things which happen inside a cloud, and we are trying to parameterize that. I still don't know what
Actually, I'm
exactly.
not able to hear. Can you speak aloud?
Okay. So, in the previous lecture, Professor Rama has told about the microphysics that happens inside the clouds, and we don't know much about it yet. And here we are talking about the convection. So there is microphysics parameterization and there is convective parameterization.
Yes.
Both of which we don't know much yet. Like we are still approximating. So how about the interaction between these two? Are the models, I mean, we have parameterization on both sides. How about the interaction between these two?
That's a good question. I don't think we fully know what is the best way of such an interaction. Microphysics happens at micro scales, right, and further smaller scales. What you are doing is writing bulk properties of to say how they influence such motions. So you are averaging quite a lot. What is the best way of incorporating such an influence? I think is an active area. I don't think there's a. Although people have tried doing it, there are not enough observations to say one way is much better than the other way. Still an active field, yeah. But models do kind of care for such a coupling and so on. So there is such a coupling between microphysics parameterization and convection parameterization or the boundary layer turbulence parameterization. That does exist, but is it the best way?
Could you just go back to the relaxation method? I was a little unclear on that.
So I was just saying that there are, so in mass flux method, you cared for updrafts, downdrafts, what were the key elements that were happening within this grid box. In the relaxation method, you say, my target profile, if you like, what happens after convection is water vapor gets drier in the lower level, it moistens above. That is the net effect of all these updrafts, downdrafts, the rest of the turbulence. So why not I take this reference profile? How do I get this reference profile? You have to make some approximations. Also validate them with the observations. I take this reference profile and I just nudge this back to the profile.
So
That's
is it
like
right
relaxing.
of me to think of it as getting a final state and initial state and then
Yes, essentially doing that. So you could say that dou z of w prime theta prime bar is equal to some mass flux time phi minus phi reference divided by tau, right? Something like that.
Thank you.
Yeah.
How reliable this decomposition is? Like we can solve this equation on 50-kilometer grid, then we are putting something in plus. So this decomposition, how reliable this is?
How reliable, what is the measure of reliability in your head?
So
Does it give good precipitation pattern? I think is one way
no.
of
So how do we think that the decomposition is so linear in the nature?
Yes, it is linear decomposition. Yes.
But whole system is quite non-linear. But here we are just decomposing in linear ways. So,
I have no a priori reason to decompose this non-linearly that tells me that that will be better than this. I mean, I agree with you that system is non-linear. Maybe this is a linear decomposition and so on. But there's no a priori reason for me to have much more faith in any other decomposition than this one.
okay.
First of all, again, regarding the relaxation time concept. So we said we are bringing it to a, what do you say?
Reference profile, yes.
Yeah. What exactly are we trying to achieve? That's something I'm not able to understand.
I think that question goes back to what is the job of convection scheme, right? Convection occurs because there is an instability in the column. Clouds want to develop. Clouds will transport mass, momentum, and heat and water vapor, if you like, such that the resultant profile is stable. Convection will stop when it's stable. So because there is an instability, convection is occurring. So the goal of such a reference profile will also be to decide what will convection do, when will it stop.
That's how the relaxation time thing comes.
Yes.
Okay.
Technically, one would like to have a nice 3D representation of cloud embedded, because this is a gross
Yes.
approximation.
It makes sense. We're getting the end result.
We are not getting the end result. I showed you how big the precipitation. I think that's the best we have done until now. And with machine learning, there are new possibilities, which I think in the second lecture we'll discuss a bit more.
So now my second question.
Yes.
So we talked also about downdrafts. So I want to ask, as compared to, because whenever we talk about a heavy rainfall event or something, we always talk about the updrafts. Even in all the reanalysis products, if we want to analyze an event, we always look at the vertical motion, and the net vertical motion we obtain is generally in the upward direction.
Yes.
So where I'm not able to understand where do we actually see the downdraft and the magnitude of downdraft as compared to the updraft. I had an idea, as you said, it needs 10 times more region. So I assume the speeds of downdraft would be much lesser than the updrafts.
Yes.
But we don't see it anywhere in any of the products.
I think you do see them in the kind of LiDAR profiles and so on. So what you could you could take a look at some of the papers on LiDAR. What happens is typically these updrafts form, they have quite fast speeds. And sometimes there are something called subsiding shells. That means fast downdrafts, almost of the magnitude of around 1/4 of the updraft happens just in the vicinity of cloud. But majority of the downdraft happens in the surrounding and at much slower pace. You could also visualize them in the large AD simulations, for example. So the downdrafts are there. You don't see them because it's not part of condensate, right? It's not visualized through a cloud.
Any online participants, any questions? Okay, if not, let's thank Vishal and